Now that we understand the historical foundations of quantum mechanics, let's dive into the fundamental principles that make quantum computing possible. We will explore four key concepts: superposition, entanglement, interference, and quantum measurement, which are the building blocks that give quantum computers their power. Let's start with something familiar. In a classical mechanics, imagine a ball moving through space. To describe its state completely, you need three pieces of information: position, velocity, and acceleration. Simple, right? In quantum systems, we use something entirely different: a state vector or wave function. This is a complex vector that contains all the information about a quantum system. To work with quantum states, we use something called Dirac notation, named after physicist Paul Dirac. Instead of writing vectors the traditional way, we use the ket notation. Here is where linear algebra becomes essential. Remember from math class that a complete set of orthonormal vectors can serve as a basis. In quantum mechanics, we use this same concept. Any general quantum state exists as a linear superposition of basis states. Think of it like describing any location on a map using north, south, east, west coordinates. The completeness of our basis ensures that any possible quantum state can be represented as a linear combination of these basis vectors. One important note: the global phase of a quantum vector has no physical significance. This might seem like a technical detail, but it's crucial. Two quantum states that differ only by an overall phase vector are physically identical. This brings us to a fundamental question: how do we measure physical properties like energy, position, or light intensity in quantum systems? In quantum mechanics, measurable physical quantities are called observables, and they are represented by special mathematical objects called Hermitian operators. Let's break this down. A Hermitian operator, which you call M, is essentially a matrix with special properties. This matrix has eigenvalues and eigenvectors that relate directly to what we can measure from a quantum system. Here's the key insight: any physical measurable quantity is represented by a Hermitian operator M. The eigenvalues of M, let's call them lambda 1, lambda 2, lambda 3, and so on. These represent the outcomes when you measure that quantity. For each eigenvalue lambda I, there's a corresponding eigenstate, ket of psi of lambda 1. If your quantum system happens to be in this eigenstate, measuring M will give you that particular value with absolute certainty. In Dirac notation, we write this relationship as M ket of lambda I is equal to lambda I ket of lambda I. This equation says when the operator M acts on its eigenstate, you get back the same state scaled by the eigenvalue. Hermitian operators have four critical properties that make them perfect for quantum measurements. 1. They are equal their conjugate transpose, which means M dagger is equal to M. 2. Their eigenvalues are always real numbers, which makes sense because you can't measure an imaginary energy or position in the real world. 3. Eigenstates with different eigenvalues are orthogonal. They are perpendicular to each other in a quantum state space. This is important. While eigenvalues are unique, the eigenvectors aren't. Non-degenerate eigenvectors can differ by an overall phase, but remember that phase has no observable physical consequence. 4. They have a complete set of eigenstates, meaning any quantum state can be expressed as a linear combination of these eigenstates. Now comes the most counterintuitive part of quantum mechanics. What happens when we actually measure something? When we measure an observable M on a quantum state, the outcome will be one of the eigenvalues. But which one? That's where probability enters. The probability of getting eigenvalue is given by the Born rule, and it's one of the foundational principles of quantum mechanics. Here's where quantum mechanics departs radically from classical physics. In classical physics, you can measure things carefully without disturbing them. You can check a ball's position without changing it, but not in quantum mechanics. When you measure an observable M on a quantum state, something dramatic happens. The state collapses to one of its eigenstates, corresponding to the measured eigenvalue. This collapse is instantaneous. It happens immediately. Irreversible. You can't undo it. Definitive. Any repeated measurements with the same observable will yield identical results. This is why quantum measurements are so fundamentally different from classical ones. The act of observation doesn't just reveal information, it changes the system. Let's make this concrete with an example that's crucial for quantum computing. Spin 1/2 systems. All particles in nature fall into two categories. Fermions, which are particles with half integer spins like 1/2, 3/2, 5/2, and so on. Bosons, which are particles with integer spins like 0, 1, 2, 3, and so on. This distinction is based on how their wave functions transform according to special relativity under the Lorentz group. All conventional matter, electrons, protons, neutrons are fermions, but photons are bosons. There is actually a third category worth mentioning, anyons, which are quasi-particles that can have spins between integers and half integers. These lead to exotic quantum statistics and are the basis of some of the quantum computers like those being developed by Microsoft. Here is where we need to be careful. Quantum spin is not like a spinning ball. A classical spinning ball has angular momentum, a vector pointing along the rotation axis with continuous values. You can spin it faster or slower at any rate you want. Quantum particles are different. Their angular momentum is quantized. It can only take discrete values. Even more strange, particles can have permanent non-zero angular momentum called spin, even when they are not moving at all. This spin is linked to particles' magnetic moment. Here's something mind-bending. Unlike classical objects that return to their original state after rotating 360 degrees, spin 1/2 particles require 720 degrees to return to their original quantum state. This is connected to the fundamental topology of quantum states that can be beautifully illustrated on a Bloch sphere, which we'll explore later. The reality of quantum spin was proven dramatically in 1922 by Otto Stern and Gerlach. They took a beam of silver atoms and passed it through an inhomogeneous magnetic field. Classical physics predicted the beam should spread out continuously. Atoms with different spin orientations should deflect, by different amounts. But that's not what happened. The beam split into exactly two distinct spots. Not a smear, not a gradient, two discrete outcomes. The silver atom spins were either up or down relative to the magnetic field with no in-between states. This experiment provided direct evidence for quantum superposition and the quantization of angular momentum. It's the principle behind how we create and read qubits in many quantum computers today. Everything we have discussed, quantum states, observables, measurements, and spin, form the foundation of quantum computing. A quantum bit or qubit can be represented by a spin 1/2 system. It exists in a superposition of 0 and 1 states. When we measure it, the wave function collapses to one definitive outcome, just like in the Stern-Gerlach experiment. But before the measurement, the qubit can explore multiple computational paths simultaneously. That's the power of quantum computing.